So yeah, I'm Manasi, and I'll be talking about some recent work about separating quantum black box reductions for succinct non-interactive arguments from falsifiable assumptions. So this is joint work with my advisor Gorian and my other collaborators Donna Dockman, Soledad, and Patrick Struck. So right, so the title is a little complicated, but basically this just means that some quantum reductions for these objects called SNARGs that I'll talk about in a bit, they just probably don't exist. So yeah, so I'll get started. So I'll first start by just talking about, proofs in computer science. So proofs are widely studied and known to be extremely useful. So for example, they've been used for the application of delegated and verifiable computation. So in this setting, there is like a client and their goal is to compute some computation C, where C is some NP computation. Here, NP is still the complexity class, so the set of languages that are efficiently checked by the verifier. And so the client has this problem that the computation is too difficult for whatever reason. And so the goal of delegated computation is that there is some much more powerful server that's saying that they can actually compute the circuit C and then provide the output to the client. Of course, we kind of want the server to actually compute the circuit C, so something that would be helpful is for the server to also provide the client with a short proof that it actually computed C. So here, this short proof that the server is going to provide is the string pi. So here you can think about the setting where you have an efficient verifier and a potentially unbounded prover that can compute circuits that this efficient verifier doesn't have the computational power to prove. And so the unbounded prover is just going to send over the proof pi that it computed this circuit C, where the output is X. So because the circuit is an NP, we know that there exists a polynomial length witness W that the prover can send over to prove to the verifier that it actually computed some circuit. But the question is, can pi be shorter than W, right? So like on one hand, the prover could send the entire computation of a circuit. I mean, like the circuit is has this polynomial length witness, so it could send over the entire thing. But because the verifier is efficient, we kind of want the witness to potentially be shorter than the entire computation. So here, like you can think about the verifier as this verify circuit that takes input the statement X and the proof pi, and then output 0 or 1. So then completeness would check if the statement X, which is the output of the circuit, is in a particular language, then the verification is going to output 1, and if X is not in the language, then the verification is going to output 0, and the verifier is going to reject. And here, so what we want is that pi to be short. So I'll talk a little bit about what short means. So this goes into this topic of succinctness. So the question that succinct proofs try to argue is how short or succinct can these NP proofs actually be, right? So if pi is too short, then the prover can just search through all of the possible proofs, just search through all the possible bit strings till it finds one that the verifier accepts, right? So if n is the length of the statement, then the statement cannot have a proof pi where pi is sublinear unless NP is in deterministic time to the little of n. And we don't believe this to be true, so there must be some sort of bound on how large these proofs have to be. So now I'll talk a little bit about the difference between proofs and arguments. So here we recall that the prover is going to send over the statement and the proof to the verifier. Here the argument is just a proof, so it's going to be also pi, but the difference is that it has computational soundness. So this was first introduced by Killian in 92 and Macaulay in 94. So true statements still are efficiently proven given some private information, which is just the witness W. And convincing proofs for false statements are hard to find without this witness W. So more formally, completeness is still like if X is in the language, then the verification is going to accept with high probability. But now the difference is in the soundness. So if X is not in the language, then the verification is going to accept with negligible probability. And now the prover is bounded. So the prover is going to run in time polynomial and some security parameter lambda. So in this setting, in which you have arguments, then it's known that pi can be short. So here we know that the length of pi is going to be polynomial, and the length of or polylog in the length of the statement and the length of the witness. So this is nice because now it's smaller than like some polynomial in the length of the statement, which is what we wanted. Okay, so this brings us to the object of a SNARG, which is a succinct non-interactive argument. So succinct just means that the proof length is polylog in the statement and the witness. Non-interactive just means it's going to be the proof is going to be one message from the prover to the verifier. And arguments, as we said, are going to be computationally bounded provers. So to show security of the SNARG, we want to rely on some hard problem just as any other cryptographic primitive. So for example, we can give a reduction from like factoring or some other hard problem to the soundness of the SNARG. And so the way we do this is through a black box security reduction. So here we model this as an algorithm, the reduction as an algorithm R, and it has oracle access to the SNARG adversary. So the idea is that R uses the adversary A, which is a SNARG adversary, to break some hard problem. So for example, for factoring, it would just be like the reduction takes input some large number, and then you output, and it outputs the factors using the adversary as a black box. So this is kind of the ideal way that we like to prove security in cryptography. And so, yeah, so there's this, so we'd like to, use some particular hard problem, but in addition, we would like to use some sort of like falsifiable hard problem, right? So in this setting, we have like an efficient challenger and some adversary, and through some interaction between the adversary and the challenger gets to decide that the adversary wins this game. So yeah, so the falsifiable assumption is just any assumption that can be modeled as an interactive game. This was introduced by Nauer in 2003. So this is most cryptographic assumptions that we use, in which the challenger can just check if the adversary has succeeded in a particular game or not. Right, so like things like LWE, hash functions, or breaking one-way functions, these are all standard assumptions in cryptography, and these are all falsifiable assumptions. So another way that we can illustrate the reduction is in which you can think of the reduction having oracle access to the adversary as like a big algorithm, and like the entire algorithm is the attack on the falsifiable assumption. So here we have like the reduction, and it uses the SNARG adversary with oracle access, and then this entire algorithm will interact with the challenger, who sends over the big number, and then the reduction will send over the factors. So I just illustrate this reduction because it'll be helpful to understand how our proof works when we give the impossibility. So classically, SNARGs have been extensively studied. So they're computationally sound short proofs, so they're quite useful. Classically also, black box reductions have been widely used. So so the reduction just uses the SNARG adversary as an oracle. And so to recap, the falsifiable assumption is just a standard assumption in cryptography. And so classically, it was known that black box security reductions from falsifiable assumptions to SNARGs don't exist. But this is what the classical setting. So we have that classical black box reductions are separated from falsifiable assumptions. And
But Manasi, sorry, just a quick question. So what would be a good example of a non-falsifiable assumption that sort of makes sense? Because almost everything seems to be, in terms of security games, right? So
Yeah, so like for example, you couldn't base SNARGs on like the hardness of zero knowledge or something like that. Because like when you try to prove like zero knowledge of something, you have to like construct a simulator.
Hmm.
So that's like an example of something that's not a falsifiable assumption. Like you can't assume like SNARGs are hard assuming the zero knowledge property of something.
Um, Wait, so you have to construct the simulator, and that's not falsifiable because uh, no, I don't
Like
think I fully understand. Can you explain a bit more? What?
yeah. So right. So when you say that like for example, if you say that like you want to base your SNARG on like 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 zero knowledge, like on the hardness of zero knowledge, then like you have to construct a simulator, and it's not something that like you have to be able to argue that you can simulate the view, right?
Hmm.
So like because you have to construct a simulator, and it's not something the challenger can easily like can just check if um like the simulator sorry, the challenger can check does like the true view look is the true view distribution close to the false view, but you need to construct the simulator in order to like output the false view or like the simulated view,
Hmm.
right? So because it's not like because constructing the simulator is not falsifiable, like
Yeah.
because the construction of the simulator itself is like a circuit, so it's not like a falsifiable assumption. So then that's why like constructing SNARGs based on like zero knowledge wouldn't be a falsifiable assumption.
Okay. Okay.
Right. So just to recap, SNARGs are computationally sound short proofs. Black box reductions are just reductions where the SNARG adversary is used as an oracle. And then falsifiable assumptions are just standard assumptions in cryptography. Um, Maybe another helpful like example of a non-falsifiable assumption is the like assuming the existence of a random oracle. Um,
Right.
like it's right. So basically, any non-falsifiable assumption is something that like maybe involves something where you have to like construct it in order to prove to the challenger that like two distributions are indistinguishable or something like that.
Mm.
Right. So classically,
This
what's
is the-
known is in Gentry-Wichs in 2011, they showed that efficient classical black box reductions from falsifiable assumptions to SNARGs don't exist. And this is assuming the existence of sub-exponentially hard one-way functions. But this is not a super, uh, this is like a reasonable assumption to make because we believe the existence of sub-exponentially hard cryptographic problems. Um, So, right. So the particular snargs that they consider in their separation are snargs in the common reference string model. So in this setting, you have a verifier and a prover, and they share some shared string. And this is a reference string, not the random string. So it could be some sort. So this like whatever shared string that the verifier and the prover share could have like a lot of structure to it. So and then another particular property that they consider for their snargs is that they have adaptive soundness. So in this case, the adversary is allowed to choose the statement after seeing the CRS. And then then if the statement is not in language, then the verifier accepts with low probability. So the point is that like you need soundness to be preserved even though the adversary is allowed to choose the statement after having knowledge of the structured CRS. So given that the SNARG has this property that where it's in the CRS model and it has adaptive soundness, then the Gentry-Wichs result holds. So SNARGs have been considered and studied for a long time in cryptography. So despite this impossibility that was shown by Gentry-Wichs, people have found all sorts of ways to go around it. In that, like maybe they consider SNARGs with non-adaptive soundness, or they consider SNARGs from non-falsifiable assumptions, or but basically they just find some way to tweak this impossibility result. So another way is that some SNARG constructions have been shown is by considering non-black box reductions as well. And yeah, so this impossibility has not stopped the like study of SNARGs, and people have like very successfully constructed really nice applications. So then a natural question is like, even though, sorry?
Sorry before you go to the next slide, in the previous slide, it said something about non-signaling.
Oh, sorry,
Could
this
you
is just from
mention
a
what this
talk
is?
that Yale College did, I think at Simons. She had it was just from a talk called SNARGs Beyond Non-Signaling.
But what has signaling got to do with SNARGs? It's a bit
This was like
curious.
signaling in like a class. It was like it's not signaling in a quantum context.
I see. Okay.
Yeah, this is just the title of her talk, but it's not signaling like in quantum.
Okay, thanks.
Yeah. Right, so then the natural question is, can quantum reductions actually provide us with the black box security that we ideally would hope for SNARGs? Right, so Gentry-Wichs proved that there cannot exist like PPT reductions, but maybe there do exist quantum reductions. Gentry-Wichs doesn't rule that out. And possible reasons that we believe this exists are that quantum reductions are known to be more powerful than classical reductions, right? So you have like a state, and then if the reduction is quantum, then it has quantum query access to the adversary. So it's able to access this A in superposition. And we also know that there exist problems for which we know quantum reductions, but not necessarily classical reductions. So for example, for LWE, we know that there exists a quantum reduction to SVP, but there does exist a classical reduction, but with significantly worse parameters. So it's well known that quantum reductions are more powerful, so maybe we can use the fact that reductions have quantum query access to the adversary in order to give a reduction from a falsifiable assumption. And so, of course, here, the assumption is now that the adversary breaks some post-quantum SNARG instead of like an arbitrary SNARG, since that wouldn't provide a contradiction. So the result that we show is no, that quantum reductions don't help, and the impossibility still holds even when you consider reductions with quantum query access. So the main result is that efficient QPT black box security reductions from falsifiable assumptions to SNARGs don't exist. And so again, we still have the caveat with the SNARGs. And also we assume the existence of sub-exponentially hard one-way functions. Right, so we still consider SNARGs in the CRS model that have adaptive soundness. So where the adversary is able to choose a statement after it sees the CRS. So the primary technique, yeah.
So before you go on to the techniques, so why is that a restriction that you're looking at SNARGs in the CRS model? So by this, what I mean is that, is it correct to say that SNARGs in the plane model with adaptive soundness are also ruled out, or because it looks like even if you're given CRS, you're still not able to construct them, right, from falsifiable assumptions. So I would imagine your result is stronger than.
Yeah, so it's like, it's stronger than considering it without a CRS, but it's not stronger than considering non-adaptive soundness.
Oh, right. And you said somehow something about the random oracles. I was a bit confused. I would have thought that the reason why a random oracle is non-falsifiable would essentially also apply to the CRS model. So how does that make sense of these two things?
So I guess the random oracle is more of like a common random string. But here we're considering like common reference strings. So the CRS here is allowed to have much more structure than the random oracle.
But in particular, it could be a random string, right? Because I thought the CRS model is more general than the common reference string model. I thought is more general than the common random string model, because the reference string could be from an arbitrary distribution. So I thought your result would also apply for common random strings, doesn't it?
Like you mean like common, so like random string with adaptive soundness?
Yeah.
Yeah, so I think that is ruled out, but what's not, but like you can construct SNARGs in the random oracle model with non-adaptive soundness.
Right. I see. So if it were the case that I'm stupid and I construct a SNARG in the random oracle model, but with adaptive soundness only, not with the. So then would that?
Yeah, so that's ruled out.
Okay.
Kind of like the important thing here is the adaptive soundness thing. The CRS part is not like super important for the. I mean, like it's the reason I pointed out is because it's like a critical like part of the proof technique. But as far as like the impossibility, because this is kind of like you want to be able to rule out the weakest thing for the strongest result. So like having a reference string is kind of like the weakest like setup setting. But then adaptive soundness is kind of a strong assumption to have on the adversary. So this is more like the limitation on the SNARGs that's considered in our impossibility.
Right. So adaptive soundness is stronger, right? Like it's a stronger guarantee, and we're saying this strong object cannot come from black box reductions of true false.
Right. And actually,
I'll ask you more questions.
Yeah.
Please go ahead. I'll ask you later. Yeah, please.
Okay, cool. Sure. Yeah. So actually, for like, there are people like one of the first SNARG constructions by Killian and Macaulay was SNARGs in the random oracle model, but they consider non-adaptive soundness. So actually, SNARG constructions in the random oracle model are known. They just have weaker soundness guarantees. So that's why like they exist. And the Gentry-Wichs result didn't rule them out. But right. So so our technique for proving this impossibility uses something called a meta reduction, which was also used by Gentry-Wichs in 2011. And so the meta reduction is what we use to rule out the existence of a QPT reduction. So now I'll explain a bit what a meta reduction is. So we first assume that there exists an inefficient adversary so there exists an adversary to break the SNARGs, but this adversary is also inefficient, right? So if you had an inefficient adversary, then this assumption attack kind of immediately breaks whatever falsifiable assumption that you have. So like, say like H is a post-quantum one-way function, and its goal is to invert the one-way function, then the challenger is going to send over H of X, and the reduction, given access to this inefficient adversary oracle, it's going to be able to invert this one-way function pretty easily. And so another way to view this is that we can consider the reduction and the challenger to be a single efficient algorithm. And then the inefficient adversary is like the oracle that this entire joint efficient algorithm uses. So, we're given oracle access to this inefficient A, and it inverts the post-quantum one-way function. But of course, we assume that the inefficient adversary was inefficient. So it's not a contradiction to actually say that like the post-quantum one-way function is broken. However, we can then consider attacks that are able to be efficiently simulated. So if you can argue that there exists some S that efficiently simulates this inefficient adversary A, then this would actually give us a contradiction and argue that there is an efficient algorithm to break the falsifiable assumption, right? So this efficient algorithm now is the combination of the reduction and the challenger given oracle access to this S instead of A. So the idea is that you just replace the inefficient adversary with some efficient simulator, and now this gives you a contradiction for your falsifiable assumption. Right, so now the picture just looks like this.
Sorry. Just to quickly clarify. So here the reduction is for the whatever gain we had for establishing the security of the initial primitive, right?
Yeah.
That's the and then the adversary was supposed to be that part I didn't fully understand. Why were we taking the adversary to be inefficient? Because I thought the whole point was that the reduction says that if there is an efficient adversary, then the reduction will be able to do something crazy. So I thought we would restrict to efficient adversaries, and I'm not sure I fully appreciate why the simulator needs to be introduced to.
So because if you first have an if you have an inefficient adversary that breaks your like SNARG basically. So you want to say that like SNARGs are based on the hardness of post-quantum one-way functions, but then you assume an inefficient adversary that breaks the SNARG. Then this inefficient adversary, when you give a reduction from the inefficient adversary to the post-quantum one-way functions isn't actually like a contradiction, because there wasn't like an efficient algorithm that does this, that actually breaks the one-way function, because it's given like oracle access to this inefficient adversary.
I see. Okay.
So it's like kind of like cheating.
Yeah. Okay. Yeah, because you want to say that the reduction itself cannot exist, right? So earlier the reduction was just saying that if there was something inefficient, it would break some widely held assumption, and now you're trying to say that the reduction itself cannot exist. And to make that statement, you have to have everything efficient and then break the whatever your one-way function
right
is. Okay.
Yeah,
sorry. Okay, thanks.
Cool. Right, so for such attacks, right, so if you consider attacks that can be efficiently simulated, then there exists an efficient algorithm to break the falsifiable assumption. And so yeah, so now the entire picture would kind of look like this, and now everything is efficient. So right, so another way to illustrate, yeah.
I'm sorry, just I got confused
no
again.
worries.
In the previous slide, so this reduction R is for the security of the initial primitive, right? Which in this case is whatever SNARG, right?
It's a reduction from the SNARG to the
whatever assumption you want to. Yeah. Right. So it's from the SNARG to the one-way function. But then this R is just talking to the efficient or whatever. Like now you swapped it, but it's just talking to the adversary, right? So I don't understand the big box around it. How is the interface matching is what I was getting a bit confused with, because the R is just supposed to talk to the efficient algorithm, right? And now it is also talking to C, like as the whole box. So is the whole box that you've written as efficient assumption attack? Is it interacting with these two entities in some way, and then also with C outside, or how do I think about this?
Yeah, so the reduction is still just going to use. So you can think of like the reduction is still given oracle access to the adversary, but the adversary is known to be like efficiently simulatable. Right. So like you could think of that reduction as like having oracle access to like an efficient algorithm instead of this inefficient adversary. And then the reduction still has to output like some sort of like response for the challenger to break the falsifiable assumption.
So the C here, that the challenger is for the assumption itself. Okay. See, so the reduction is okay. So sorry, I just got very confused. Okay, sorry.
Yeah,
makes sense.
No worries. Okay. Yes, there's a lot of moving parts. Cool. Okay, any other questions? Cool. Okay, so another way that we can think about these types of like simulatable attacks are through this concept of meta reductions. So the point of a meta reduction is we want to rule out the existence of the reduction. And we do this by arguing that like there exists an inefficient adversary, and it can be replaced by an efficient simulator. So to a quantum polynomial time distinguisher D, it cannot distinguish between access to this inefficient adversary versus an efficient simulator S. So a meta reduction says that a simulatable attack implies that there cannot exist a black box reduction. So this QPT-D is going to like query the oracle, and it's going to query the oracle on some security parameters, some CRS, and some random coins. And what we want to argue is that this distinguisher cannot distinguish between oracle access to the inefficient adversary or the efficient simulator based on the responses on these input queries. So that's kind of like the hard part of meta reductions, is to show that there exists this simulatable S, or the simulator S for the inefficient adversary.
And what you're calling D here is just the collection of the boxes, or is D going to use R and C in some non-trivial way?
No. So D you can think of as just the reduction and the challenger and their interaction. Okay. So like the reduction is really like going to be the one querying on these inputs.
So when I think of any QPT D, I'm thinking that C is fixed and I'm spanning over all possible R's. Is that the?
Yeah, that's right. Okay. Right, so now I'll talk a bit about how we construct the inefficient adversary and the simulator. Okay, so we're going to, so let L is just an NP language, and we can define distribution families over yes instances and no instances. So yes instances are L, no instances are L bar. Right, so here, yeah, so if X is in the language, then L is a distribution over X is in the language, and L bar is the distribution family over statements not in language. So we first assume that there exists L, and that's supposed to say L bar, that are quantumly sub-exponentially hard to distinguish. And then, right, so this goes back to our original assumption that we had of the existence of sub-exponentially hard one-way functions. So like assuming that there exists this L and L bar that are sub-exponentially hard to distinguish is basically assuming the existence of sub-exponentially hard one-way functions. So let S be, so like let L star be an augmented distribution family that's now over valid statements and proofs. Right, so we can first sample an X and a witness, so a statement and a witness, according to the language, and L star is going to be this a family of distributions over statements in the language as well as some auxiliary potentially correlated information pi. The only restriction on pi is that it's going to be short. So the efficient simulator for us is basically just going to run the strategy of an honest prover. Right, so this is exactly what an honest prover would do, is it would sample a statement and a witness, and then given the witness, it's able to generate a short proof. So X and that proof pi is the whatever the honest prover outputs, and the efficient simulator is just going to do that. And now we want to argue that this is actually indistinguishable from an inefficient adversary. Right, so let L bar star be the augmented distribution family over invalid statements and proofs. So when X is not in the language, L bar star is going to be the distribution over X not in the language, and then also false proofs. So proofs for false statements, essentially. So it's clear that, so if we had L bar star and L star, then, and we knew that they were indistinguishable, then we would be done, right? Because then we would say that the inefficient adversary samples from this L bar star distribution, the efficient simulator samples from this L star distribution, and they're indistinguishable, so we can argue that A and S are indistinguishable. But it's not clear a priori why this false distribution that's indistinguishable from the true distribution should even exist. So that's what our proof shows. So we first start off by showing sample indistinguishability, which means that given for like a fixed index of the distribution family, then given classical queries, A and S are indistinguishable, right? So the distinguisher is going to query on some security parameter, CRS, and some coins, and then given these input queries, then the outputs that the adversaries have are indistinguishable according to a single classical query that the distinguisher is allowed to make. And then we upgrade this to showing oracle indistinguishability. So given now that the distinguisher is allowed Q quantum queries to a fixed index I of the distribution family, then the outputs of the adversary in the simulator remain indistinguishable. And then we finally show oracle indistinguishability of the entire distribution family. So then we just argue that for every index in the distribution family, the two outputs are indistinguishable to each other for distinguishers that are allowed to make Q many quantum queries, where Q is polynomial.
Mansi, sorry, so
yeah.
I kind of have like a few small questions. So the simulator you're saying is outputting from this language x comma pi, and wait, so x. So x is the actual language that we want to decide, right? Like x is the yes or no instance. I guess it's the yes instance, but for the case of L, right? And we're assuming that it's efficient to generate x and pi if you're choosing x. Is that?
So it's efficient if it's true. right? So like if X is in the language, then because it's a SNARG, we know that like if X is in the language, then there's this prove algorithm that you can use on input like X in the witness. So that's like yeah.
Okay, I
So
think
like
the augmented part I got. Okay, yeah, there it is. Okay, sorry.
yeah. So when like the honest thing that the approver is going to do is like given that it's an honest prover is it'll be able to generate the witness, and then given the witness, it can generate the proof. But
Right.
generating a false proof is like an inefficient task. But our adversary
A
is
false,
inefficient, is allowed to be inefficient here.
right? So a false proof, meaning like a valid proof for a false statement, right?
Right.
Is that?
Yeah.
Okay.
Right.
A
So
valid proof for a false statement, and is it clear that this exists? Because
it right, because we're considering arguments. So like we know that the probability that like if X is not in the language, then it'll accept is like small. So we know that there exists some false statements. It's just that they might be hard to find, like computationally difficult to find.
I see, interesting. But that's not the case for well, like for example, if you have, I see. Okay, makes sense. Yeah, because so this is specific to arguments, right? Like, so if it was actually proofs,
Yes.
like I don't know, three colorability or whatever, then it's not clear that for a false statement you can produce a valid.
Exactly.
Or for a sorry, yeah, okay.
Right. For
Yeah,
a
I
false
cannot
statement.
convince you that it cannot be colored, right? Like there's no short necessarily a short proof.
Right.
Okay. Thank you. Yep.
Yeah. So the fact that it's an argument is really crucial here.
I see. Okay, thank you.
Mm-hmm. Right. So we finally get to this final point where the distinguisher is allowed to make a polynomial amount of quantum queries to the entire distribution family, and we can preserve indistinguishability. Yeah. So okay. So maybe I'll briefly go through each one of the steps. So sample indistinguishability has kind of been previously shown. It's implied by a previous result. It was called the quantum leakage lemma. So yeah, so basically this just shows that S epsilon sample indistinguishability of the distribution. So here S refers to the size of the distinguisher, and epsilon refers to the indistinguishability of the two distributions. So it's basically saying like for size S distinguishers, it has advantage epsilon for distinguishing two distributions D1 and D2. So the leakage lemma just says that if you have two distributions, Lx and Ly, over where x and y are just n-length bit strings, then if Lx is S epsilon indistinguishable from Ly, then there exists a possibly inefficient circuit C such that rho xb is S star epsilon star indistinguishable from rho yb, where S star and epsilon star are polynomially related to S and epsilon. So here, another restriction that we have is that rho b, x here, and c of y are L qubits, where L is like kind of a small amount of quantum information. Right, so here S is polynomial and S star, and then epsilon star is O of epsilon. So right, so the indistinguishability doesn't change by too much, is what the so yeah. So the leakage lemma is basically saying that the indistinguishability doesn't change by too much when you allow some like small auxiliary quantum information.
Wait, so
maybe
what is C here? C is a circuit or
yeah. So the way like you can think about how this applies to the SNARG setting of like you can think of like the qubits as being the proofs. So like in our case, it's like a quantum circuit generates the proofs and then like, oh yeah, it generates the proofs, but in our case, they're classical. So like they just measure the circuit. So you can think of this as being like the short proofs and then like X and Y being the true statement and the false statement. So like in our case, we started off by saying that like L and L bar were S epsilon indistinguishable. And then the leakage lemma is saying that there exists some circuit C such that the proofs that you generated using the true statements are S star epsilon indistinguishable from the proofs that you generate using the false statements.
Now I'm still getting a bit confused with how to think about C. So in the LL bar language, how do I interpret C? Is generating the witness, the proof from the witness? Oh, sorry,
C is the proof for the false statement.
Nice. And why is the problem instance? Is it? Or?
Yes. Why is the false instance?
The false statement. Okay. And so C is inefficient, right, in a sense,
yeah.
for us.
Yeah. So yeah, so what this is saying is that like if you have a guarantee that like your original distributions are indistinguishable, which in our case we do, right? Because we assume that L and L bar were indistinguishable, the true and false statements were indistinguishable.
Right.
Then given some like correlated auxiliary information, the two distributions remain indistinguishable. Is all this is saying.
Right.
But this is indistinguishability with respect to classical queries. So this is why it only gives us sample indistinguishability, and also sample indistinguishability of a single query. So now we need to upgrade this to oracle indistinguishability, right? So this was like quantum queries for a particular distribution index. So this follows from Zhandry's small range distribution technique. So the issue here is like the distribution is going to so the distribution can the distinguisher can query on some input state, and then the adversary or the simulator is going to respond in superposition. So it'll evaluate F in superposition and then send that state back.
Right.
Right. So here, just to explain a bit about what small range distributions are, if people aren't familiar. So right. So the small range distribution basically just will take like a particular so like if you have two distributions, D1 and D2, then you can argue that D1 and D2 are as epsilon and sample indistinguishable. Then small range distributions allow us to argue that they're S prime, epsilon prime, oracle indistinguishable. So the idea is that you can just sample a particular set of values from the range and then use those smaller set of range values to simulate quantum query access to the entire distribution. Right, so like what this picture is trying to show is that like you have all these points in your domain in X, and they're all going to be mapped to some value in the range. And for us, we just argue that like a subset of the range values are sufficient to simulating quantum query access to these distributions. And so these are the bounds that we get for that. Right, so yeah, so here, like, this is what the small range distribution is kind of simulating, is that there's like this small subset of values R, and that allows us to simulate quantum query access. And then finally, we get to oracle indistinguishability of the distribution families. So we consider oracles of this form. So it's like index quantum query access, so controlled on the index and the input X. The adversary is going to output some indexed value f of X on like for that particular index. So yeah, so it's a simple hybrid argument over all possible indices. So in our case, each index is a possible CRS. Right, so yeah.
But doesn't sorry, when you're running the hybrid argument, I thought you could only run it poly many times, right? At least the naive versions. And here it looks like your index might be exponentially many. So how do you handle that?
Yeah, so we do some complexity leveraging. So we basically start with the assumption of a sub-exponentially hard problem that is like the
I
hardness,
see,
where
I
the
see.
hardness of the problem is more than the number of possible CRSs.
I see, I see.
Yeah, so when we hybrid over the CRSs, it is exponential, but it's just a smaller exponential, and it's fine.
Got it. Got it. Thanks.
Right, so the final statement is like if we have two distribution families, D1 and D2, over a set Y, if D1 and D2 are sample indistinguishable, S epsilon sample indistinguishable, for all I, then D1 and D2 are S star, epsilon star, oracle indistinguishable, where they satisfy these bounds. So here K is the number of CRS. But yeah, so like Atul, you pointed out, the number of CRS is exponential, but in our case, S and epsilon are also going to be larger exponentials than K. Right, so, okay, so this is actually exactly what you brought up. So sub-exponential hardness of an L and L bar imply the existence of super exponentially hard distributions, M and M bar. So for a large enough polynomial M of n. And so in our case, since I is a CRS, we choose a hardness such that the CRS doesn't scale with the statement length. And then this is sufficient for showing indistinguishability. Yeah, so to recap, what we just showed is the existence of this L bar star. And yeah, so then this is sufficient for showing that there exists a simulatable attack that cannot be distinguished by any quantum polynomial time distinguisher D. Yeah, so some future directions. We would like to also rule out SNARGs with quantum proofs. So the issue is that we relied on Zhandry's small range distribution framework for functions. And so in order to rule out SNARGs for quantum proofs, we would also need to have some sort of framework that rules out SNARGs where evaluating the proof is not necessarily just a function, right? It could also be a unitary. But since Zhandry's small range distribution framework doesn't handle unitaries immediately, then we can't directly apply this framework to rule out quantum proofs. Other interesting directions is like showing that there exist meta reductions for other primitives, since I don't think meta reductions have been extensively explored in the quantum setting. Yeah, I think I'm about out of time, so maybe I can end here. Otherwise, I can also continue talking about like SNARGs with quantum proofs.
Yeah, we have about half an hour more, so yeah,
Oh, okay.
it's an hour and a half. So don't worry about that.
Oh, for some reason I thought it was an hour. Okay, cool. Yeah, so I can talk a little bit now about how one might rule out SNARGs with quantum proofs. So, right, so now if you have a quantum proof, then the proof is generated by some unitary, or yeah, so it's just a quantum state now. And right, so one issue is that it's not really clear what the right model is, right? So like maybe now you want to allow unitary access to the adversary. Yeah, so as opposed to in this case where we just allowed like generic quantum query access where the adversary is just going to evaluate some function in superposition. And it's also not clear, like, should we be enforcing, like, how should we be enforcing the actions of the adversary if we should be enforcing anything at all? So, like, should we require that the adversary measures certain registers before evaluating the proof? Like, for example, when the distinguisher queries the adversary on a particular statement, like, should the adversary have to, like, measure the statement and show the proof for a particular statement, or should we be allowing, like, a arbitrary statement to be chosen? Yeah, it's not clear what exactly the right behavior is. And additionally, maybe there is some shared entanglement between the prover and the verifier now that the prover can generate a quantum state. So yeah, it's just not immediately clear what the right model is to rule out SNARGs with quantum proofs. Because now your adversary is quantum. Like your simulator also has to be quantum. Right, so the setting is also a bit different. So we'd now be considering SNARGs for QMA as opposed to NP. So now the verifier is also going to be a quantum circuit. So for QMA, this is going to state for every X in the language, there exists a quantum witness psi. And yeah, so this, based on this psi, then the prover is going to have to generate some proof rho. And that's what we want to say either exists or doesn't exist.
But
Another
once you
issue,
want
yeah.
but I remember seeing some papers that were showing succinct arguments for QMA. It was like using some compiled games or something else. Am I misremembering?
Right.
Do you know anything about this? Or?
Yeah, so those are succinct arguments, but we want to show succinct non-interactive arguments. So
Oh, it's
all
the
those
interaction
constructions
that
just
you're.
use interaction.
Oh, oh, I see. I see. Got it.
Mhm.
Got it. And one small thing I wanted to ask was I think I didn't still fully understand. So you said your argument. So argument is a technical term. Damn it. Okay. So your so what you were saying was it only applies to the common reference string model,
Yeah.
and but if you try to run the same argument, right, as what you described, but with a random oracle, what part breaks in the analysis? Is it the number of indices one has to sum over? Is that what breaks? Because I guess one can think of a random oracle as a common reference string, but like you have lots of indices you can query, right? So is it that step that breaks, or?
No, I don't think it doesn't break. Like if you consider like the random oracle but adaptive soundness, that's what's ruled out.
So that is still ruled out, you're saying. Okay, okay. Because if
Yeah.
you're efficient, you cannot possibly query more than whatever, exponentially many. Yeah. Oh, sorry.
Right.
Cannot query. Yeah. Okay, okay. I see. Okay. So, and where did we use adaptive soundness in your proof?
Yeah, so the adaptive soundness was used for oracle indistinguishability. So for us, like we could first construct these small range distributions in
Mhm.
order to simulate the adversary. But this involves like sampling many values from the range, and the range in our case is the statement and the proofs, right?
I see. So
So
it depends on that. Okay.
right, so the adversary is going to be able to view the CRS and then also view this set
Right.
of values that we sampled. So there we use adaptive soundness.
Right. Right. Okay. Thank you. Thank you.
Yeah. Right. Okay. So another issue with using our framework to rule out SNARGs for QMA is the quantum leakage lemma. So actually, even in our case, there's kind of this issue where the quantum leakage lemma doesn't really hold, or it's not known to hold, if the distinguisher is allowed quantum advice. Right. So just to show the leakage lemma again. So this is the statement. So it's only known that this statement holds for distinguishers with classical advice. In our case, this wasn't really an issue because we needed to apply the leakage lemma for classical statements and proofs. So for us, even though we sample a polynomial amount of statements and proofs, all of those values are classical, and we provide those samples as classical advice to the reduction. So it's not really clear now if the proofs are allowed to be quantum, then does this still work? Because the distinguisher is now, like the entire reduction is going to have some sort of quantum advice, and it's not clear that the quantum leakage lemma holds in this case. Because remember, the distinguisher is a combination of the reduction and the challenger. So actually, even in our case, we don't rule out reductions that have quantum advice. It's only reductions that have classical advice, but also it's not like, at least I personally don't really know of any reductions that only go through because of the existence of quantum advice. But for the case of QMA, because the samples now are going to contain some quantum information, it's not clear that we can apply the leakage lemma.
Right.
Yeah. So yeah, so improving this to have quantum advice. I've like looked at it a bit. I haven't extensively looked at it, so maybe it's possible, but I'm not sure. Right. So one way that you might be able to, so at least to fix one of the problems is you can consider unitary small range distributions. So here U is now a distribution of a unitary operators instead of functions, and X is still a finite set. And so now you can consider the oracle that maps X and Y to U sub X applied to Y. And so, right, so the same small range distribution approach still holds here. So you could hard code polynomially many circuits for the short proof that are generated from like a small subset of the range of possible unitary operators. But note that here it's not a general model because this requires that the statement register is measured. And this goes back to this issue I brought up of it's not clear what the right model is to rule out SNARGs for QMA, because this is actually not a general model. Here we required that the statement register was measured, and based on a particular X, then there was like a particular unitary that was applied to the output. And it's not clear that this is something that we should restrict the adversary into doing. Yeah, so I'll end here. Yeah, and I'll take any other questions.